Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
So today we'll be doing something completely different, well, at least mostly pretty different. It's Bayesian inference. So we're only going to do the basic introduction to Bayesian inference, but it's a really common method these days, especially. Whenever you have a spam filter in your email, or whenever your bank calls you because I think they had a fraudulent transaction, there's no certainty obviously about those, but they're using a Bayesian filter to come up with guesses as to whether there's something that needs to go on there. And why are they using this new method called Bayesian inference? Why are they not using classical statistical inference? Well, classical statistical inference is what we've done so far, and it's often called frequentist. Frequentist statistics or frequentist inference comes down to a belief that the only meaningful use of probabilities is for an experiment that you could in principle repeat in identical circumstances as many times as you like. And that point of view says that under frequentist statistics, there's no meaning to a probability other than just if you did this as many times as possible independently, what fraction of the time would it happen? That is the meaning in frequentist statistics. And that's why we were careful in the context of saying frequentist statistics. We had frequentist confidence intervals, things like probability that lower end of the confidence interval less than theta less than u equals 1 minus alpha. We did that quite often. That's an example of frequentist statistics, a frequentist confidence interval. And the key thing to know here is that theta is non-random. Because after all, if your experiment is something like finding the true proportion of disease in a population, the true proportion of disease in the population is not random. It's just the proportion that exists. It's just inaccessible. So there's no meaning to ask what is the probability that the proportion is here versus there. It's just one value. We just don't know what that value is. So in the frequentist point of view, the upper and lower end points of that confidence interval are the only random thing. Theta is not random. It's just every time I did the experiment, I'd come up with a different number, different pair of numbers for the confidence interval, and 95% of the time, that pair of numbers would contain the true value. That's the meaning in the frequentist world. So Bayesian inference starts when you get a little bit more relaxed and less uptight and stop insisting that, it's meaningless to say the probability of theta equals 3 or the probability that theta is in a certain range. If we don't insist on the strict frequentist meaning, if we don't insist that everything has to be an experiment I could repeat infinitely many times. So I'll just say the philosophy is probability is only for, I'll just say experiments. Okay, experiments which are shorthand for something you could repeat independently many times. Okay, that's the philosophy of frequentist statistics. So now we're talking about philosophy of Bayesian inference. And the philosophy of Bayesian inference is much more broad. It says that, sure, you can use probability to reflect experiments. Those are the ones that you can repeat as many times as you like and find a long-run proportion. But also, probability just, can be a description of degrees of certainty. We talked a little bit about degrees of certainty or degrees of confidence, or let's even call it this way, belief, to show that there's something very subjective about it. Degrees of certainty or degrees of belief about unknown parameters, even if this couldn't be reflected by let me say, repeated as an experiment. Now, there is still a constraint to this. The axioms of probability still hold, so, which we did at the start of the course. They have to hold. So one way to think about Bayesian inference, and we'll get into the nuts and bolts in a moment, but one way to think about it is it's the kind of school of thought where you no longer require these to be actual physical experiments. You can just imagine kind of thought experiments. Or another way to think about it would be alternative universes. In what proportion of all the alternative universes would this be true? So it's a less stringent interpretation of probability, and it can lead to allegations of subjectivity. Subjectivity means that the answer you get will depend on your subjective state of belief at the beginning. So let's, to get into the nuts and bolts of it, let's start with the first idea of Bayesian inference is, well, the first idea is a prior distribution. But first let's review Bayes' theorem. Okay, so, because there is a reason it's called Bayesian inference. Bayes' theorem, as you would recall, it's about talking about the chance of being in a particular one of mutually exclusive categories given you observed some piece of information. So this will be a new interpretation of the formula we already know. So the probability of that is the probability of that VI unconditionally, probability of A given VI, divided by the same thing added up over all possible categories BI. The BIs are the mutually exclusive categories. Sum j equals 1 to n, probability of Bj, probability of A given Bj, where, of course, in this description, B1, B2 up to Bn are mutually exclusive and exhaustive events. Mutually exclusive means that Bi intersect Bj is empty set, and exhaustive means union of all of them, j equals 1 to n of Bj is the whole sample space, which I thought to make. So that's a review of what Bayes' theorem told us. We already proved this. It's not very hard to prove, of course. You just go from the definition of conditional probability, because on the bottom you have the probability of A. Using the law of total probability, it was decomposed as shown. And then what is the interpretation? I have, so B1 up to B2 up to Bn are the underlying states of the world, and we're in one of those categories, and we don't really know which one, but we know they have certain probabilities to start with. And so let's say, category A, categories green, blue, and red have probability 0.2, 0.3, and 0.5. Okay? So green, blue, and red. So in other words, for instance, that might be for a bag where I don't know which balls are in there. And then when you take an observed piece of information, that will improve your knowledge of the situation. So if you're just selecting one ball from the bag, then you can look at A might be the event that the ball is red. And then you have a new updated idea, which is the conditional probability of Bi on this observed event. Now, the way you should interpret this is this even has a name, posterior probability of Bi. Posterior means after you observe the new information. And this one has a name, which is the prior probability. So A is the observed piece of information, and then P of Bi, that would be called the prior probability of Bi. So to get from the prior to the posterior, you multiply by something. So let's write it that way. Probability of the so posterior, Bi given A, is equal to the prior times a new factor, probability of A given Bi. Now, in principle, I'm sort of reweighting by the conditional probability of seeing that observation given category Bi. But I have to make sure that these probabilities still add to 1. If I just multiplied probability of Bi times this, then they wouldn't still add to 1. So I divide by the appropriate normalizing constant, j equals 1 to n, probability of Bj, probability of A given Bj. So you notice that denominator is the same for all I. It's a constant. So this is just the unique constant that you need to normalize these new things by in order to get a posterior. So just labeling each of these things. That would be what you call the prior probability. This is the posterior. And then this conditional probability of A given Bi, that's often called the likelihood. And it's the likelihood in the same sense we've already seen in the maximum likelihood estimation. So essentially, posterior equals prior times likelihood. And the only correction you have to make to make that an actual mathematical equation is you have to divide by the constant, which is this thing on the denominator, and that's the only way to make it add up to 1, because probabilities all have to add up. So that's the review of Bayes' theorem. Now let's also review. We'll see that we've seen Bayesian statistics in many guises already. The next thing that we'll review is joint and marginal and conditional densities. Now, you notice I'm focusing on densities. I'm going to focus on the continuous case for most of today. Everything for Bayesian stuff is pretty much the same, discrete and continuous, where in discrete case you use mass function, continuous case you use density function. This one is pretty much just like the mass function case, you're adding up numbers. So since we've already done that adding up case, I'll just do the density case. But what is true for discrete with adding up mass function is the same true for continuous integrating density function. So let's review joint and marginal conditional densities. I'm just going to review a formula that should be very familiar to you. The density of, I'll even do B and A matching previous before. The density of B given A, these are continuous variables now. Joint, conditional equals joint divided by marginal. F A B, A comma B, divided by F B. Okay, so far so good. This was a definition that we gave. Another way to write the same thing, well, one thing that's interesting in Bayesian is to relate the posterior distribution to the likelihood. Now, why is this condition thing called a posterior distribution and this one called a likelihood? Well, it's a matter of interpretation. We're going to apply this in the case where A's are observations. So the A is like the sample, the X's that we're used to. And the B's are more like the parameters. Okay? So in the discrete case, we thought of a parameter that only had a finite number of possible values, 1, 2, 3, up to n. Effectively, your parameter would be which one of the B's are you in. That's in this very simple Bayes' theorem example, you've got one parameter which just takes discrete values, 1, 2, 3, up to n. That's your parameter B. So your posterior distribution is a distribution on the parameter. You get to it by starting with your prior distribution on the parameter, which is your subjective belief of which parameter is most likely, or what the distribution of parameters is. Then you multiply by the likelihood. The likelihood is the only part of this that is objective. Prior is subjective. You're like, oh, I think theta equals a half is the most likely, or I think it follows a normal distribution. That's subjective. Posterior is also subjective because it incorporates the prior. The part that is objective and matches what we did in frequentist statistics is the likelihood, and that's the same likelihood as before. There's an intriguing feature that I'll repeat later. You remember the likelihood function. I said that you can sort of omit multiplicative constants from the likelihood function if you like. That also applies in Bayesian statistics, because if you take this likelihood function and just put a constant in front of it, it doesn't matter because the same constant will occur in the denominator. So that property where you can ignore multiplicative constants in the likelihood will also be true for Bayesian inference. So let's get to this second review, joint and marginal conditional distribution. So I want to get this in terms of a prior, which is of course FB of B. I'll remind you that we're thinking of B as the parameter. This is just a way of thinking in this case. B is the parameter. FB given A of A given B. Oh, that of course should be B given A. If I want the parameter given the observation, I get joint over marginal, which is FB of B times conditional F A given B of A given B. Now on the denominator I have the same denominator term, but I remember that it is possible to write the marginal in terms of the joint. In fact, remember the marginal is defined. There might be many definitions, but one definition is just you take the joint density and integrate out the variable you don't want. Integral from, I'm going to say minus infinity to infinity. Obviously, if the true range is restricted from that, you'd have to restrict that. But in principle, it could be from minus infinity to infinity. of the joint. And once again, the joint can be written as a two-variable function, but I'm going to write it in this form. So fb of b, fa given b of a given b, db, dA. A is the variable that I'm trying to eliminate. Yeah, I've done it. Yeah. Okay. Yeah. Let's fix everything up. A on the denominator because I'm doing conditional on A, and that means I am doing dB. Because I want to get something of A, I integrate out the B. So that's now correct formula. Now this should look very, very similar to what we saw here. In fact, it's the same. That's just the discrete form, and that's the continuous. It's even possible to have B discrete and A continuous, or A discrete and B continuous, and it's just kind of the obvious thing. If you have a density, you integrate it. If you have a mass function, you add it up with a summation. So those things say the same thing. And so let's write it in terms of posterior, in terms of prior. FB given A, B given A. This is the posterior. To be precise, this is the posterior density. Okay, that one you might call a posterior PMS because it's discrete. So the posterior density is equal to the prior density FB of B times this factor, which is the likelihood. Now remember, likelihood is a fancy word for the density function given you know the parameter. So fa given b, b is the parameter that we know of a given b. And then the likelihood is always normalized out by dividing by the appropriate sum or the appropriate integral. And that's just to make sure that the posterior density actually is a density. It has to be a density, so it has to integrate the 1. So this is just what it has to be to make that work. Fb of b, fa given b, a given b. So nothing really new here. And so the likelihood in each case is normalized, and you do posterior equals prior times likelihood. And that tells you, this is really an incontrovertible probabilistic argument for how you should update your personal view of the probability of B. If B is a parameter and I think, oh, well, I don't, for instance, let's do the first big example, which will be I'm going to use A and B as before, but the parameter, okay, is going to be, there is this unknown parameter B, which has to be in the range 0 to 1, which is a proportion, okay? And we're going to have A is the observation, okay? And how is the observation depending on the parameter? We would say that A as the distribution. If we were doing it frequentist way, we would just say what the distribution is in terms of the parameter, binomial NB. N will here be known. Okay, so we're not doing anything funny about it. So if we were doing it frequentist, if we were doing it in the frequentist world, we would write A has the distribution binomial NB, and B is the unknown parameter. Since we're not doing it in the frequentist world, let's put an A given B as the distribution binomial N. Okay. So, as a matter of whether I use capital B or lowercase b, clearly capital B is the random variable and lowercase is the value, but it means the same thing. So in the Bayesian world, we tend to write it this way. So we know that B01, so is to do Bayesian inference, what we really need is a prior on the parameter B. And And this is where the level of subjectivity comes into. But sometimes you can try to disclaim that subjectivity by saying, oh, well, I'm not really partial to one theta, one b over another. So let's take the prior. Remember, the prior is another way of saying the marginal on b as a distribution. Let's say that it's uniform, 0, 1. Uniform on the right. That's, sometimes this is called an uninformative prior. This is often something people want to do when they want to make the argument that their Bayesian analysis is not too opinionated, it's not too biased, because, oh look, I'm making every b equally likely. It's arguable whether or not that's the case, because this is equally likely with respect to the normal measurement, but there will be other scales along. For instance, if you took log b instead of b, then that would be a different logarithmic scale, which would not be the same. Uniform on a logarithmic scale is not actually possible because it goes off to minus infinity, but you could have another distribution on the logarithmic scale. So anyway, this would be arguably described as an uninformative prior because it's not particularly biased one way or another for b. And then calculate the posterior density. Okay. So it all depends on your parameter. If your parameter is discrete, you call it a posterior PMF. But normally our parameters are not discrete. It's very common for them to be continuous. So normally we're calculating posterior density. The posterior density is f of b given a. Now a is actually a discrete variable, but it doesn't matter. When people are doing this in practice, it's very common to omit the subscripts because it saves right. But for the moment, I'll include it. So the posterior is naturally fb of b. That's the uniform density, which is actually equal to 1 on the relevant scale. And then I have to multiply by, I'm going to slightly modify what happens here. PA given b, A given b, divided by the integral from, okay. I guess it's okay for me to say minus infinity to infinity because I'll put the density fb of b, PA given b of A given b. Now, compared to my paradigm that I put here, the only thing that's changed is anything to do with A is a mass function instead of a density function. But that's the way to do it. Mass is discrete, density if it's continuous. And so let's be a bit quite clear about this. That is equal to 1 on the appropriate region, which is 0 to 1. So 1 times the conditional probability. Now that's, typically we would not even call that a conditional probability, we'd just call it the probability. But in the Bayesian world, we consider that a conditional probability. It's just the binomial probability. So n choose A, b to the power A, 1 minus b to the power n minus A. Okay. That's what it is. So it's 1 times n choose A, b to the A, 1 minus b to the power n minus A. And then on the denominator I have to do the same thing. I integrate from 0 to 1 because that's the valid range b. 1 times n choose A, b to the A, 1 minus b to the power n minus A. Now, and then db. Okay, so that's what it is. For those of you who've been doing some exercises about calculating densities, and beta densities particularly, you'll recognize this quite frequently. So the first thing to notice is that common factor of n choose A drops out on top and bottom. That's a manifestation of what I said with the likelihood function. You can consider this to be the likelihood. And just like for normal likelihoods, if there's a constant that is known, you can just remove it from top and bottom because it occurs there and it occurs there. So that likelihood, well, the posterior density is b to the A, 1 minus b to the power n minus A. Then I have to divide by integral 0 to 1, b to the A, 1 minus b to the power n minus A db. I'll cut to the chase, and you remember that those are the, if b is x, b is the variable, that's a beta density with parameters a plus 1 and n minus a plus 1. So this is actually the density of a beta. So gamma of 2 divided by gamma of A plus 1, gamma of n minus A plus 1, multiplied by, so that's the constant that's out in front, b to the A, 1 minus b power n minus A. Of course, 1 is less than 0 is less than b is less than 1. And that is equal to gamma of n plus 2 divided by gamma of A plus 1, n minus A plus 1, b to the A, 1 minus b, n minus A, 0 less than b or less than 1. So posterior is, when you're asked about the posterior distribution, you can often give a precise answer of that. B given A, we just write it this way. Given the observation A, which was the observation from a binomial NB, the posterior is now a beta distribution A plus 1, n minus A plus 1. Okay, that's starting from if prior, to reiterate on B, is B has a distribution uniform 0, 1. Now, anyone remember, as a little party trick, what is uniform in terms of beta? That's actually a particular beta. If you're uniform 0, 1, that has the same density everywhere. A beta has b to some power, 1 minus b to some power. So those powers have to both be 0. Now, the power is actually the parameter minus 1. So it's beta 1, 1. That's right. You remember you have x to the alpha minus 1, 1 minus x to the beta 1. So uniform 0, 1 is actually the same as beta 1, 1. So somehow, now I just want you to kind of observe, this is something special to beta has gone on here. If beta, like effectively we had parameters 1, 1, the first parameter has increased by the number of successes, A, and the second parameter has increased by the number of failures, n minus A. That's actually a general property of this prior family. So a family of distributions, this is a little vague, but it turns up in a lot of contexts. A family of distributions for a parameter theta is called a conjugate prior. Okay, so the conjugate prior is not just a single distribution, it's a whole family of the parameter priors. A conjugate prior for an observation x. So all of a sudden I'm going back to more traditional notation, theta for the parameter and x for the observation, whereas b was the parameter and a was the observation. Conjugate prior for an observation x. If the posterior of theta given x is a member of the same family. Okay. That seems kind of, so family is a bit vague. So this is particularly a parameterized family. The parameters in the context of beta are the two alpha and beta. They could be multiple. So not only does, when you have beta 1, 1, is your posterior beta a plus 1, n minus a plus 1, it actually follows, whenever you have a beta prior, you get another beta prior as the posterior. Sorry, whenever you have a beta prior, you get a beta distribution as posterior, and that posterior is more informative. It's incorporated more data. So let's do, to formalize that example, I'll write it as a fact. Okay. If I'm now going to do the parameter calling. I'm going to call the parameter p because that's natural for a probability. So p has a distribution of beta, alpha, beta, and beta. Let's say the observation given p. Okay, I'll make the observation A as in the previous case. A given P as the distribution binomial N. So N will be a known thing, P. Then, so this is, I don't need to put this word in here, but the prior is given this, and then that's the part that is objective. You could call that the likelihood, is the binomial likelihood. Then the posterior P given A, see the conditioning P given A gives you the posterior, is beta, and it's the same pattern as I said before. Alpha was, so remember prior has something to do with subjective knowledge. Well, you know, alpha is sort of, I'm pulling alpha units worth to the left and beta units worth to the right. Another way to think about the prior is that, well, it's sort of as if I think, from previous experiments, I think about alpha out of alpha plus beta times, it would have been a success. Now, you know, beta 1, 2 is not the same prior as beta 2, 4. They have the same expectation, because of course, you have this great thing about in Bayesian analysis, you can just take the expectation of a parameter. Totally forbidden in frequentist, but I can do that. It's alpha over alpha plus beta. So there's actually lots of choices of alpha and beta that do that. So long as you move alpha and beta in scale to one another, that would do it. And the ones with higher alpha and beta are more specific. And this will also show when you have this new observation, A given P, in binomial on P, it'll be beta alpha plus A, beta plus n minus A. Okay, so now let's prove this fact because it's a good exercise in doing calculations. Now, the first thing about Bayesian analysis is you know, it just follows from the definition that the posterior density is actually a density. So keeping track of all the constants, first of all, you don't need to keep track of the constant in the likelihood because it vanishes from top and bottom. Secondly, when you're doing known densities, you can, for the moment, omit the constant in those because if you recognize the density, you'll recognize what constant is needed. So I like to use this proportional to symbol to do that. So f of p. Now, you'll notice I'm also omitting the subscripts on density functions just to save a lot of writing. So the prior density is, of course, f of p. Now, okay, well, it's exactly gamma alpha plus beta divided by gamma alpha gamma beta p to the alpha minus 1, 1 minus p to beta minus 1, 0 less than p less than 1. That is the prior density. Now, I'm just going to do a little cop-out and say this is constant, alpha plus beta are constant, alpha and beta are constant, and I will be able to recover the appropriate constant at the end, so let's not bother with gamma functions. It'll make everyone a lot happier, especially on the exam, that's the right. So let's just use this proportional to symbol. Everyone's seen it in physics and stuff, no doubt. It just means we'll figure out the constant later, it doesn't matter for now. So proportional to p to the power alpha minus 1, 1 minus p to the power beta minus 1. Okay? 0 less than p less than 1. Okay, so that's what, it's enough to have the prior is proportional to that. The likelihood, now remember the likelihood, you can call it the likelihood of the parameter p, but that's actually the same thing as the density of, remember the likelihood is the density given p. It's not actually the density of p, because the density of p doesn't make sense in the frequentist framework. It's the density given p. Density of A given p is, once again, now I could give it to you exactly, n choose A, p to the A, 1 minus p to the n minus A. But let's not bother with that. Let's just say that this is proportional. Well, let's save a bit of effort. It's proportional to p to the A, 1 minus p to the power n minus A. Now, of course, that n choose A is there, but when we're doing the likelihood, it's a constant with respect to p, so I can still do it. Okay, so the integral that means the posterior density, and I said density, it's easy. If you notice the notes from previous years, the author of those notes actually uses f and p interchangeably. I'm trying to use p for density, so that's for mass function. So this is, whether the likelihood is a mass function or whether it's a density, it'll work the same way. So the posterior density, f of p given A, is proportional to the prior density f of A times the likelihood. of A given P. Why do I not even have to, okay, so that's proportional to, the prior was already here, P to the alpha minus 1 minus P to the power beta minus 1. And then the likelihood, let's just put in this thing, P to the A, 1 minus P to the N minus A. Now people are probably, and I'll just put in, it's always nice to put in the range of P's because that can throw you out. If you didn't have the right range of P's, you would get the wrong constant when you integrated that. So I think, although it's tempting always to drop the range of parameter values, it's good to keep that in there. So it's certainly a lot easier to write that than to write all the constants. Now people are probably feeling a bit queasy now because there was an n choose A there which I just unaccountably dropped. Now the reason that n choose A can be dropped is because that same thing, its probability of A given P, I think that same thing will be dropped out from the numerator and the denominator. So anyway, you can double it. When you have this likelihood term, yeah, so just to get back to the general theory of posterior is obtained by doing prior times likelihood, normalized out. But what this denominator is, it's just whatever it has to be to make the product of these two things into a density. It's just whatever it has to be. So we're going to forget the constant and figure it out at the end because there's only one constant it could be. And you notice that there's only one particular value of A that goes in here. It's B that's integrated. It's not A that's integrated. So there's no harm in saying the n choose A that's been integrated out of the bottom. The A was the same on the numerator and denominator disappeared. So if you want to avoid all that discussion, feel free to omit constants from both the prior and certainly the likelihood. If you omit the constant from the likelihood, you don't even get a proportional sign. If you omit the constant from the prior, you might have to recover it at the end. But okay, so let's do that. So that equals P to the power alpha plus A minus 1, 1 minus P to the power N beta plus N minus A minus 1, 0 less than P less than 1. And thus, posterior distribution of P given A as the distribution beta alpha plus A beta plus N plus A. Now, that's known straight away because the only thing that has a density that's proportional to this is beta alpha plus A beta plus N minus A. And we know the constant in the front should you need it, but we won't plug it in. So we've proved that. So what's said, the summary is P, which is beta with parameters. Now, of course, it's a whole family. Alpha and beta is a whole family. Is a conjugate prior to an observed, or an experiment, an observation, A, which has distribution. Now, because we're doing Bayesian, we tend to say A given P has an observation distribution binomial NP. Okay? Has conjugate prior, and posterior is, so the posterior is P given A, the observation is A given P, and that has a likelihood. P given A, which is beta alpha plus A beta plus N minus A. Now, what is the meaning of the conjugate prior? Alpha, beta. What is the meaning of this? Well, okay, it's subjective. It's very subjective. It's, of course, you can just draw that as a certain density depending on the beta parameters. If the parameters are high enough, it'll look like a little lump within the range 0 to 1. That's what beta looks like. Unless the parameter values are very small, the beta looks something like that. The higher the parameter values, the narrower it is. You get a lower and lower variance. So already by going from prior to posterior, you get higher parameter values. You get a more focused estimator. And you get a more focused estimator. So what is the meaning? There is a meaning of this conjugate prior, even though it's totally subjective. The meaning is something along the lines of have already seen. I put this in inverted commas because there's many ways to interpret it. You have already seen alpha minus 1 successes and beta minus 1 failures after a uniform P uniform to start with. Why is that? Because if I start with P uniform to start with, that's beta 1, 1. How do I get, as a posterior, you see, prior and posterior is just for one experiment. You can use the posterior to one experiment as the prior to the next experiment. You get more and more information, and as you update, you keep doing that. So if someone tells you, oh, our prior is now beta alpha beta, well, one way that they would have got that quite logically is to start with a uniform prior, and then they would have already seen alpha minus 1 successes and already seen beta minus 1 failures. So you see this is totally antithetical to the frequentist point of view. The frequentist point of view says, you're not allowed to use information from previous experiments in this. This is an independent experiment. It has no bearing on it. That's quite different from the Bayesian point of view. The Bayesian point of view says, well, you know, we've got some experience with this. We've seen pretty much, and if alpha and beta are large, we've seen pretty much a ratio of alpha to beta successes to failures. And the size of alpha plus beta is pretty much how many observations worth we've seen. So if you have alpha plus beta observations already, and then you add another n observations, it'll get a whole lot more precise. So that conjugate prior has a sort of meaning, but that's just one way you could have got it. You could also just have said, this is what I believe. Now, if you don't use a conjugate prior, you can use a different density. It doesn't have the easy update property. You could easily imagine that you get some horrible formula for the updated density. And if that's the case, the calculations don't work nearly as nicely. So that's why we focus on conjugate priors and conjugate posteriors if we can. So I just want to talk about, to go full circle, we were talking about frequentist confidence intervals. So what I want to talk about is how do you actually do Bayesian inference. Oh, before I want to do that, remark, the Bayesian estimators, if I just want point estimators, there are two ones you might often do, which are the posterior mean, which is expected value of theta given the observation, which, you know, how do you do that? You just integrate theta posterior density d theta, right? You can calculate that. You get a posterior density. To do this, you'd have to make sure to put the constant in. When you do it proportional, for that actually to integrate to the right thing, you have to have the correct constant. So put it in. And then there's also posterior mode, okay, which is the theta that maximizes, the theta hat that maximizes the density of x, theta given x. Okay? So we can do one example in the case where the theta given x has the distribution beta, alpha plus a, x was the observation, beta plus n minus x. The f of theta given x is proportional to theta to the alpha plus x minus 1 minus theta to the beta plus n minus x minus 1. And I want to differentiate that and set to differentiate and set to 0. That will find that. Okay, maybe I won't go through it here. That's a good exercise. So for a function t of theta, sometimes you might not be able to do just theta. The best estimator, point estimator, just for practical terms,